In this lesson, we're going to try and combine two big ideas. One's from last unit, one's from this unit. So in the last unit, we examined discrete situations, things that were always whole numbers, things we could count, and we're looking at successes. In this unit, we're looking at continuous things, things that we measure. Well, it turns out we can actually put those two things together. There are lots of different situations where if you gather discrete information, things you can count, and you graph it out, it kind of almost looks like a normal approximation, or basically normal. And the reason we like to think about doing things in a normal way is we can examine a lot of cases very quickly, especially if we're using technology, as opposed to having to do each situation individually and put them all together. So we'll look at an example here to sort of maybe clarify that a little bit. So multiple choice test has 200 questions, each of which may be answered with 1 of 5 answers. What is the probability of getting exactly 100 questions right? Now, this is a perfect example of a discrete situation. Okay? They're right or wrong. I can count how many right answers I get. And because they're independent and repeated, it really is a binomial situation. So from last unit, our formula was n choose x, the number of trials, n. X is your number of successes, times p to the n minus x, how many times you want to be correct, how many times you want to be successful, and q was your number of failures and how many times you want to do that. In this situation specifically, the first part of it, we're looking for exactly 100 successes. So there's 200 trials, 200 questions, and I want to get somewhere in there 100 of them right. My probability of success in any one question is 1/5 or 0.2. I want to be right 100 times. My failure would be 1 minus success. I want that to happen 100 times. Now, if you try this with your calculator, you'll probably get math error. Your calculator is actually not powerful enough to do this. But if you take a graphing calculator, just to remind ourselves, and we'll be using graphing calculators for this lesson. Okay. We want to do 200. The choosing buttons under the math menu there, 100. So 100 correct ones of the 200. I want to be successful 20% of the time. I want that to happen 100 times. And I'm going to fail 80% of the time. And that's going to happen 100 times. The probability I get exactly 100 correct is pretty small. 2.33 times 10 to the negative 21. Scientific notation, or in other words, put a 20 zeros out front. 5, 10, 15, 20. That's the likelihood you get exactly 100 correct multiple choice questions by just guessing. Now that's not exactly hard to do. We can use our formula as long as we remember how to work it. Just typing it into our calculator is the only challenge there. But if I look at the second half of this question, what's the probability of passing this test by randomly guessing at the answers? I come into a new situation. Passing the test means getting at least 100 right, which means it could be exactly 100, or it could be 101 answers right, or 102 answers right, or so on and so on and so on, all the way up to 200 answers right. That's 100 cases to go through, each of which has to use this formula, each of which is going to have a tiny little answer like this one. That's kind of time consuming. That's a lot of button pushing. Somebody might think, well, let's do it the indirect way. Let's get rid of the cases we don't want. Well, what does it mean we don't want? We don't want 99 or 98 or 97 or all the way down to 0. Well, again, that's still 100 cases to go through. That's a lot of button pushing, each of which is going to have a tiny little answer like this one. So how do I avoid this situation? Well, the way I avoid it is by applying my new idea of a normal distribution. And so here's some ideas let's go through first. Okay. If you have a binomial situation, things that are repeated and independent, they can often be approximated. That's a key word there, okay? And it's an approximation. It won't get you the exact same answer, but it'll be pretty close. using a normal distribution. The advantage of this is, thinking about a normal situation, a graph, I don't have to do each calculation separately. I can do intervals, add them all together pretty quickly. The technology is going to do the work for me. Okay. But there are some things we have to work through first before we can actually apply the situation. It won't always work. It doesn't work when there's a small amount of data. To be honest, it only is statistically reasonable if NP and NQ are both greater than 5. Okay? N is still the same thing. N is our number of trials. P is still our success. And Q is still our failure. Those things aren't going to change. Same as before. But I have to test out if this is going to work before I try it. Otherwise, the answers I get won't be approximate. They'll be completely wrong. Okay. Additionally, if you're thinking about my normal distribution here, we know our normal distribution is based on the mean and standard deviations, right? 68, 95, 99, those are based on standard deviations. But if I go back to our kind of question for a second here, we don't have those things. They told us how many questions there were, they told us success and failure, but they don't give us a mean and standard deviation. So we need to approximate them. Okay. To approximate them, the mean is n times p. Now, the good news is we have to calculate that anyways to see if this is statistically reasonable. So I'll have an extra piece of information. And the standard deviation is the square root of n times p times q. Now we haven't calculated that. That's not this thing up here. It's something different. So we'll have to calculate that separately. So two sets of calculations. One to see if it's reasonable, one to actually start working with it. Okay, and then one more big piece of information. The whole idea of discrete things is you're trying to find the probability of getting something. The probability of getting 10. The whole idea of normal distributions is that you're wanting intervals. You don't have equal signs. So to correct this, we use something called a continuity correction. What that is a plus or minus 0.5 adjustment to get rid of the equal signs. Okay, so for instance, if I want to get exactly 10, no, I don't want 10. I want between 9.5 and 10.5. That way, the only discrete whole number I can get is 10. I've turned something that was an equal sign into a interval. Let's say it was I want to be greater than or equal to 10. Well, I can fix that by saying, well, let's go down as far as 9.5. Okay, that way I can, again, whole number, only one I'm going to include will be 10. Because 9.5 and bigger, the only whole numbers there are 10, 11, 12. And then the last circumstances, what if I want to be less than or equal to 10? Okay, I would actually have to go up to 10.5. I want to include 10, but I got to get rid of the equal sign, and I do that by making a 0.5 adjustment. Okay, so if I go back to that question again, this big, long, crazy question, I don't want to do all these different cases. How can I do this with my new technique? Well, I want to get at least 100 right. So for a continuity correction, I want to get at least 99.5 questions right. I can't get 99.5. Go and get 100 or 99 or 98 whole numbers right. But if I go to 99.5, the only whole numbers I'm including are 100 and above. Okay, I got to see if I can actually do this first. N times P. N is my number of trials. P is success in any one trial. That's 40. That is definitely bigger than 5. Okay, NQ, 200 times 0.8. That's 160. Ooh, definitely bigger than 5. So I know I can do my approximation. My approximation needs two things. It needs the mean, which I've already figured out, and it needs the standard deviation, which I have not figured out. My standard deviation is the square root of n times p times q. So it's a new combination of numbers. Make sure you're using the right ones. and make sure at the end you actually square root it. So this should be about 5.67. Or 66, I guess. Sorry. Okay, so graphing calculator time. Okay, we want to do our normal distribution, so second vars, number 2. Okay, we want to start at 99.5. We want to go all the way up to 1E99. Our mean we just figured out was 40. Our standard deviation was 5.66. I'm going to paste that in, and we're going to get an answer of 3.87, and notice at the end there the E negative 26, that's scientific notation, so 3.87 times 10 to the negative 26. Okay, so by just guessing at this, random guessing at every question, 200 of them, the likelihood of passing, not so good. 25 zeros, and then 387, pretty small. But that's not the point of this question. The point of this question is I've saved myself all the time and effort of typing in all of these things independently and separately, and did it by using my normal distribution, much faster. Okay, we're going to try a couple examples, just 2 here, make sure we can have this figured out, and then you guys can try some stuff on your own. So a box holds 240 eggs. The probability that an egg is brown is point. Okay. Find the expected number of brown eggs in the box. This goes back to last unit. Expected value is n times p when things are binomial, discrete, repeated, independent. 240 eggs, those are discrete things, right? You can count how many eggs you have. Just because one egg is brown doesn't mean the next one's going to be brown, so they're independent. And we're doing this repeatedly, 240 times. So 240 times 0.05. P is our probability of success, the likelihood of finding a brown egg. Oh, I should expect 12 eggs. On average, that's how many eggs I'm going to get, right? That's my mean. Okay, try part B here. The probability that there are exactly 15 brown eggs using the binomial idea. So this is our old one. There's 240 of them. The likelihood I find 15. The likelihood of success, 0.05. I want that to happen 15 times. I want to fail 95% of the time. And 240 minus 15 gives me 225. Into our calculator we go. And you should get approximately 0.0733. The likelihood we find exactly 15 brown eggs using our old idea, the binomial distribution. We want to try this with a new idea, using the normal approximation. Before I do that, I got to do my little check. Is NP greater than 5? Well, we already figured that out, right? That's right here. So definitely. NQ, 240 times 0.95. That comes out to 228. That's definitely bigger than 5, so I'm good to go. I can do this. I just have to do it now. Okay. I want to get 15. Ooh, that equals 15. I can't do that with normal stuff. I need to make an interval, so I need to go from 14.5 to 15.5. I also need a mean and a standard deviation. Now the mean, we've already talked about that. That's NP. My standard deviation, haven't found that yet, the root of N, P, Q. Need all those things together. And if you type that in, you should get 3.38. Okay, graphing calculator time. What do we got here? Second vars, number 2. We want to go from 14.5 to 15.5. Our mean we just said was 12. The standard deviation we just calculated was 3.38. I'll paste it in there. We'll get an answer of 0.0795. 0.0795. Okay, before we move on, let's talk about this. What did we find out? When we use the binomial method, 0.0733, 7.3%. The normal way, we get 7.9%. Remember, they should be close. They're not going to be exactly the same. That's why it's called an approximation, approximately the same. They're pretty close to each other. To be honest, the more data you have, the more cases, the closer they get. Okay? It is reasonable, we tested that, but it's not going to be exactly the same. But it saves me a lot of work sometimes. Maybe not so much in that case. Let's look at the next one. Find the probability there are at least 10 brown eggs. Okay, if I want to do at least 10, I'm looking for greater than or equal to 10. That would be 10, 11, 12, 13, 14, 15, all up to 240. Or indirectly, get rid of 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. That's a lot of button pushing. But if I use my approximation, I just look for more than 9.5. Well, this is going to be pretty quick. All I have to really do is change my lower to 9.5. My upper is going to be 1E99. Okay, my mean is my mean. My standard deviation hasn't changed. That's pretty fast to type in. My answer is 0.770, or 77% of the time I'll get at least 10 brown eggs. That's way faster than doing all those separate cases. And that's my whole idea here. I want to save myself time. Is it going to be exactly the right answer? No, but it'll be really close. Okay, you guys are going to try one. So this is our last example. Pause it, try it yourself, see if you can figure it out. If not, start the video again, see what you've messed up. Okay, a mail solicitation. It's a mailing. It's sent out to 1,000 people, each of whom has a 9% chance of responding. What's the probability that at least 85 people respond? That's a whole bunch of cases. 85 all the way up to 1,000. I don't want to do that. Okay. But I know I might be able to approximate this by using my normal distribution. Let's check it. N times P, I need that anyways, because that's my mean. So N times P, 10 times 0.9, that's 90. And Q is definitely going to be bigger than that. That's 910. Definitely bigger than 5. We're good to go. I've already found my mean. It's right there. Haven't found my standard deviation yet, though. Standard deviation will be the root of N P Q. Don't forget the square root part. It's the part you always mess up. You should get 9.05. Okay, graphing calculator. Away we go. Second var is number 2. Hey, our lower boundary, 84.5. My upper boundary, you can leave it at 1E99. My mean, I just found it was 90. My standard deviation was 9.05. Enter, enter, paste. And I get 0.7283. So it's a pretty good chance that at least 85 people will respond. 72% chance. If we do part B, what's the probability that between 90 and 100 respond? So I'm going to go from 90 up to 100, but I can't do equal signs, so I correct it by saying 89.5 up to 100.5. Back to my calculator. Number 2, I got to change my lower bound. And I'm going to change my upper bound. Mean and standard deviation are all the same. And I get 0.3990. Or in other words, 39.9% of the time between 90 and 100 will respond. Okay, that's the normal approximation. I use it to save myself time of doing a whole bunch of individual cases. But to do it, I have to check first, is it going to be statistically reasonable? So NP and NQ have to be greater than 5. Not equal to 5, greater than 5. Both of them. Okay, some questions to try. Just a couple there. Make sure you know what you're doing. Test them out. If you're stuck on something, come see me. That's otherwise the last lesson of the unit.